This lesson covers the closely related topics of aircraft stability and weight and balance. The stability aspect is a fairly theoretical discussion. The weight and balance is a very practical skill. So stability refers to the tendency of an aircraft to fly straight at a particular speed without active pilot control. If an aircraft has too little stability, then it's difficult for the pilot to keep it flying straight and level. If the aircraft has too much stability, then it's difficult for the pilot to make it change speed or turn. Stability depends on the center of gravity being in the correct place. So we need to consider the weight of the occupants and any other added weight to make sure that the center of gravity is where we intend it. We'll start by defining what we mean by static stability and dynamic stability. Then I'm going to go one axis at a time through the different axes, and starting with yaw stability, roll stability, and finally pitch stability. Then we'll talk about how we calculate weight and balance, which is an important characteristic for making sure we have good pitch stability. Static stability refers to the tendency to return to an equilibrium point if something is disturbed from the equilibrium point. So as illustrated here on the left, one example of something with positive static stability would be a ball rolling in a valley. At the base of the valley is this equilibrium point where the ball will tend not to roll either direction. But if that ball is pushed one direction from the equilibrium point, it will tend to roll back downhill toward the equilibrium point. The second example is negative static stability. Although there is an equilibrium point at the top of the hill, if the ball is pushed a little ways off the equilibrium point, the ball will continue to roll farther away from the equilibrium point. And the final picture is neutral static stability, where the ball won't necessarily be pushed either direction, toward or away from the equilibrium point. So once we have a system with static stability, then we get to the question of dynamic stability. So a system with static stability, the object will return to its equilibrium point, but it won't necessarily stop there. In many cases, it will continue moving past it and then go back and forth in oscillatory motion. So a system with neutral dynamic stability, like this top one, that oscillation will kind of go on indefinitely at about the same amplitude. Positive dynamic stability, which is the second picture here, there's oscillation, but the amplitudes of the oscillation get progressively smaller, and after a while, it's back in its equilibrium situation. Negative dynamic stability refers to a situation where each oscillation gets a little bit bigger than the previous one, and eventually the system kind of goes out of control. So our ideal situation is to have positive dynamic stability, which in fact requires positive static stability. So in the coming slides, I'm going to talk about the aerodynamic mechanisms by which airplanes have stability properties. And in those slides, I'm going to assume that the aircraft has a conventional aircraft configuration with the tail in the back. You may encounter some airplanes like this canard airplane pictured here that have very different configurations. These aircraft actually have very good stability properties, but the explanations for why they have those properties are somewhat different than what I'll be covering in this lesson. So of the three axes, the yaw axis is probably the simplest in terms of the mechanism for stability. Recall that yaw refers to whether the airplane is pointed in the direction it's moving. So in this picture we see an airplane that is pointed in the direction it's moving, with the black arrows indicating the direction of the airflow. Suppose that some disturbance causes the airplane to yaw so that it is not pointing into the airflow anymore. That airflow will strike the vertical tail at an angle, and when it does that, there will be a lift force off the vertical tail that pushes the back of the airplane back around like a weather vane and yaws the airplane back so that it is once again pointed into the airflow. Next, let's consider roll stability or lateral stability. Notice that the terminology here isn't totally consistent. The vertical stability refers to rotation around the vertical axis. Lateral stability actually refers to rotation around the longitudinal axis, and as we'll see, longitudinal stability refers to rotation around the lateral axis. So let's consider an airplane here that was flying straight and level. The red vectors indicate the lift of the left wing and the right wing. Now let's suppose that something causes the airplane to bank. So if we don't make any rudder inputs, the airplane will enter a slip. It will start moving kind of sideways through the air. That slip causes a restoring roll moment, and there's a few different effects that contribute to that, which we'll cover individually. Dihedral, tail position, wing position, and wing sweep. So when you look at an airplane on the ground, in some aircraft you'll notice that the wing tips are a little bit higher off the ground than the wing roots. That's true in many aircraft, but not all. When that is true, we say that that aircraft has some degree of dihedral. So with an aircraft with dihedral, then that horizontal component of the airflow tends to hit the bottom of the upwind wing, and it tends to hit the top of the downwind wing. So the angle of attack gets increased on the upwind wing and decreased on the downwind wing. That changes the amount of lift so that the upwind wing increases in lift, the downwind wing decreases in lift, and that creates a moment tending to roll the wings back towards level. So notice that as the horizontal component of airflow encounters the fuselage, it has to flow around the fuselage. Some of the air goes above, some of the air goes below. That affects the flow of air around the wing roots. So on a high wing airplane, like pictured here, that means that the air encountering the wing root portion of the upwind wing has a higher angle of attack, and the air encountering the downwind wing will have a lower angle of attack. That creates a restoring moment that tends to make the airplane roll towards level. For a low wing airplane, that effect is opposite. So the low wing airplane will often need more dihedral because it has to overcome this tendency to be less stable. So in this slip, the horizontal component of airflow will hit the tail. In the vast majority of airplanes, the tail sticks up above the center of gravity. So in that situation, that sideways force on the tail, which is the same one that was giving us our yaw stability, will also be tending to roll the airplane back towards wing level. The last of these effects is the wing sweep effect. When an airplane has a significant amount of wing sweep, where the wing tips are behind the wing root, then in a slip, the air tends to strike this upwind wing more directly and strike the downwind wing at kind of a glancing angle. That causes the upwind wing to produce more lift, the downwind wing to produce less lift, which will tend to roll the aircraft back in the correct direction. Notice that a large amount of wing sweep is not a common feature on general aviation airplanes. So the dihedral effect and the wing position effect, which tend to be the two strongest contributors to roll stability, both rely on this relationship between angle of attack and lift. They both rely on the idea that one wing is going to get a higher angle of attack and the other a lower angle of attack, and that's going to result in a change in the amount of lift produced. This graph shows how angle of attack is related to coefficient of lift, which is proportional to the amount of lift that the wing produces. Well, in the normal operating range that we fly in, there is a very strong relationship between angle of attack and lift coefficient. However, if we're operating near the stall angle of attack, then that relationship changes. It first flattens out and then actually starts to lift decreases with angle of attack when you get past the stalling angle. Therefore, when an aircraft is very close to stall, these two contributors to roll stability kind of stop working, and aircraft tend not to be very stable and roll right near the stall. This is why it's common when you do a stall for one wing to drop. So all four of those mechanisms that we discussed for positive static roll stability involve some span-wise airflow that happens because of the airplane being in a slip. But when you are in a coordinated turn, you don't have a slip. You don't have that span-wise airflow. So those mechanisms are not present in a coordinated turn. In fact, when you're in a coordinated turn, another effect comes into play, which is that the outside wing in the turn tends to travel a further distance than the inside wing. That means the outside wing has a higher airspeed, and more airspeed will cause it to generate more lift than the inside wing. That causes negative static stability in the roll direction, which is called an overbanking tendency. So you'll often notice that in a coordinated turn, especially a steep turn, you'll notice that once you're established in that turn, you actually have to hold the ailerons against the turn in order to maintain a constant bank angle. So we've talked about static stability in both roll and yaw. Now let's talk about dynamic stability. So the dynamic modes for yaw and roll are actually closely coupled to each other. So we'll talk about them together. The most common mode is called a Dutch roll mode. This involves, like, if you have a right roll, then part of that right recovery will end up causing a little bit of a right yaw disturbance, and then that recovery from that right yaw disturbance actually causes a little bit of a left roll, and the process goes back and forth a little bit. One of the certification criteria for certified aircraft is that the aircraft have positive dynamic stability for Dutch roll oscillations. So your certified aircraft, these Dutch roll oscillations should not get out of control on you without you having to do anything. Moving on to pitch stability. First, let's look at the forces that are acting on the airplane when we are in our equilibrium state. So here we have an airplane flying along straight and level. The center of gravity is located in front of the center of lift of the wing. So to balance the forces, the tail has to produce some downward lift. So the tail is actually pushing down, and the wing has to generate a force that's actually a little bit greater than the weight of the aircraft because it's counteracting both the weight and that tail force. So now let's consider some disturbance pitches the aircraft to be more nose up. So that pitch change makes the angle of attack greater on the wing, and it makes the angle of attack on the tail be less negative. So the tail force goes down and the wing lift goes up. Both of those things tend to create a moment around the center of gravity, which tends to push the nose back down. So that gives us our static stability in pitch. Now, during the time that the aircraft is recovering back to its original pitch attitude, the lift on the wing is going to exceed the weight of the airplane. The forces will not be balanced during that time. So during that time, you will get a change in direction of motion where the airplane starts to climb. And once it starts to climb, it tends to start slowing down. Now let's consider the dynamic stability in pitch. There are a couple of different oscillating modes that aircraft have in pitch. There is a short period oscillation and a long period oscillation. The short period oscillation is something that is in the order of 2 to 5 seconds to oscillate with the nose up and down. And the certification criteria for airplanes is that the aircraft must have positive dynamic stability for this mode throughout the whole approved center of gravity range. So as long as you've got the center of gravity within the approved range, then the pilot doesn't need to do anything in order for this dynamic mode to settle down and everything go back to equilibrium. When the pilot does try to make corrections, the pilot can actually create a dynamic instability because the pilot's reactions oftentimes will be too much and too late. So the nose starts pitching up. By the time the pilot reacts to that by pushing forward on the yoke or the stick, the nose was already coming back down due to its own stability, and the pilot's input just causes it to go past the equilibrium mode by even more and create an unstable situation. This is called a pilot-induced oscillation. So the best thing to do if that starts happening is just to hold the controls steady and let things settle out. There's also a long period oscillation. This is related to the tendency of the aircraft to start climbing and slowing down while it recovers to its pitched attitude. This oscillation mode is much longer. The certification criteria is simply that the airplane not be too divergent to make it too difficult for the pilot to control it. So some pilot intervention may be needed to deal with that, but it is not difficult to do. So what happens if the center of gravity isn't where it's supposed to be? So if the center of gravity is behind the design range, that means it's too close to the center of lift, or in an extreme case, actually behind the center of lift. As a result, that static longitudinal stability is decreased. The control forces tend to be lighter. When the control forces are too light, that lack of feedback through the controls tends to make it more difficult for the pilot to control pitch. In an extreme case where the center of gravity is way back of the design range, recovering from a stall condition may actually become impossible. With the center of gravity further back, the amount of downward force on the tail decreases. So that has the beneficial effect of reducing the amount of lift that the wing needs to produce, because recall that the wing needs to produce lift both to counteract weight and to counteract that tail force. So decreasing the amount of lift that the wing needs to produce will decrease the induced drag, and it will also decrease the stall speed and improve the cruise performance. So what happens if the center of gravity is too far forward? Well, the effect we were just talking about in terms of the amount of lift that the wing needs to produce goes in the opposite direction. The wing will need to produce more lift because the tail will be producing more downforce. So airplane performance gets worse. The controls get heavy. You have to pull harder. You need a lot more use of trim. If you're in an extreme case, you may actually not have enough control authority to do your round out during your landing. So now that we understand why it's important to make sure that the center of gravity is in the acceptable range, let's talk about the calculations that you should do in order to verify that that's true. So weight and balance is calculated using a form like this, where we have a row for each different weight, and for each different weight we capture the weight, the arm, which means the distance of that weight from some datum point, which is chosen for your aircraft design, and the moment. The moment is the weight times the arm. So the first weight is the empty aircraft. We'll obtain this information from the weight and balance form that's required to be in the aircraft in order for the aircraft to be airworthy. Sometimes the weight and balance form does not indicate the moment directly. Sometimes it indicates the center of gravity, which is another term for the arm of the empty aircraft. And you have to do the multiplication. You have to multiply the weight times the arm to get the moment. The arm for the other weight locations is in the pilot's operating handbook. So this is the location of these different loading locations. So next you need to determine how much weight you've added in each of these locations. So you have to have a good guess at what each occupant weighs and how much baggage you're putting in the baggage area. For fuel, you should use 6 pounds per gallon of fuel. So you add up all the empty weight and the weights of these things you've added, and you get a number. That is the loaded weight of the airplane. Then you need to determine the loaded moment. So you multiply each weight times its corresponding arm to get the moment for that weight. Then you add those all up to get the total loaded moment for the airplane. And then you do a division. You divide the total moment by the total weight, and that gives you the loaded center of gravity location. So having calculated the loaded weight and the center of gravity, the next question is that acceptable? So the pilot's operating handbook will have the information you need to know what the acceptable range is for both weight and center of gravity. In some cases, it may be just an upper and lower limit for center of gravity, or as in this example, the forward limit for center of gravity may actually change depending on the weight. So in the example we just ran, we had a loaded weight of 2,534 pounds and a center of gravity of 91.1. If we find that point on the graph and it's within the boundaries, then we are safe to fly with that loading. So good exercise to do with your flight instructor is that you should get your pilot's operating handbook for the airplane you're using for your training and get the information from the weight and balance form that's in the airplane. And you should do a few sample weight and balance calculations. Can you fill the tanks if you've filled all the seats? In many general aviation airplanes, if you put a reasonable sized passenger in every seat, you don't have enough useful load left to fill the tanks up with gas. You need to know if that's true and for your airplane that you're using. Try to think of like the worst case loading for aft CG that you can imagine and run those calculations and see if it's out of the CG range. Usually lots of luggage would be the worst aft CG. And then also try to think of the worst case forward CG and see if that's out of range. That would usually be when you have maybe a very heavy front seat passenger.